Shall we get started, Chris?
Yep. Okay. So thank you very much indeed for attending our first webinar of the UK Catalysis Hub. We've been astounded, I think, by the level of participation in this event. So thank you very much indeed for doing this. It's getting close to the number. I think it's probably quite close to the largest number of people we've had at a UK Catalysis Hub event. So no pressure, Duncan. But it's yeah, it's really fabulous. It's also amazing to see the variety of people we have here. You know, we've got people from all over the world, and we have academics and students and postdocs and industrialists, and it's absolutely fabulous. Thank you very much indeed for taking the time to do this. So my name is Chris Hardacre. I'm current director of the UK Catalysis Hub. I should say that we would like you all to mute yourselves if you haven't done, apart from Duncan, of course. And we would also like to say that the webinar is being recorded and we will upload it hopefully onto our website. Josie, is that what we're going to do? Yeah, okay. And so people can look at it afterwards. But if you obviously don't want your videos to be shown and your kitchens and bedrooms and whatever it might be, wherever you might be, to be on the recording, then obviously if you turn off your video, then that would be fine. We've been doing some of these at the university, and they work very well. And so what we're going to ask you to do is, after Duncan has given his presentation, then we will ask you to use the chat functionality, and that is, if you go down to the bottom bar, you'll see that there's a mute and stop video and participants, but there's a chat functionality. And if you use that chat functionality and you type in your question, then Josie, because I will have to leave in a few moments, unfortunately, but Josie will then field the question and say who's asked the question, and then let Duncan obviously answer the question. And obviously, if there are follow-ups, then we can do it that way, and so on. And that should work pretty well. We will obviously have a recording of all the questions that have been asked as well via the chat, and we can take it from there. We're planning to do a number of these using members of the UK Catalysis Hub to tell us about their research, in particular about research that is applicable to industry and how that's been taken forward, and with the view of engaging the entire community and to promote the research that we're doing and to show people what we can do, and also to involve other people in what we're doing too. The UK Catalysis Hub is not meant to be an exclusive organisation. It's supposed to be inclusive. So if you're not already involved in the Catalysis Hub and you would like to be in the future, then if you would email Josie, I think is probably the easiest thing to do, if that's okay, Josie. If you'd
yes.
like to email, and Josie may put her email address on the chat function. If you'd like to email Josie and let her know what you're interested in. At the moment, we have 4 main themes of the Catalysis Hub. We have a theme that is associated with core activities, which is developing some data analysis, rapid data analysis with the central facilities, and also some new reactors with the central facilities. We have another theme which is associated with developing and designing new catalysts, which Catlo organises, and that again has elements to do with neutron scattering, laser facilities, and the diamond light source. We have some activities associated with water and energy, which is the theme that I lead, and then the theme that Matt Davidson leads is associated with the circular economy. And so we will continue to have those. We have a proposal round which ends at the end of July. So if you're interested in submitting proposals to that, then please have a look at the UK Catalysis Hub website and take part. And of course, because of the lockdown we're under currently, we have decided to postpone our normal summer conference, and it will become a summer winter conference, and so hopefully we'll be back all in good order at that stage, and not having to social distance perhaps too much, given that we will hope to run a normal conference in December. So I think that's all I was going to really say. I don't need to give any sort of health and safety notices about where the fire exits are or where the toilets are, so that's okay. I'm sure you've got those all in hand at your own establishments. And so without further ado, I'd like to introduce you to Duncan Wass. Duncan is the director of the Cardiff Catalysis Institute, and he is going to give us a talk about some of the work that he has been doing with industry. And so, Duncan, the floor is yours, and I hope it goes very well.
Thanks very much, Chris. I think it's really important in these strange times that science keeps moving forward. And I think just the number of participants that we're seeing today is showing that there's a real appetite for that to happen. I was reminded recently from one of my former students of a story about Newton. So in 1666, it was the time of the Great Plague. All of the universities were closed because of this, and so Newton had to go home to Woolsthorpe Manor. And while he was sort of sitting in quiet contemplation during this break, it's when he started to formulate his calculus and theories of gravity and theories of optics. Now, I'm not saying we should maybe go for the lofty heights of Newton's great achievements. I think not least because he had a nice apple tree to sit under in his garden rather than having to homeschool the kids. But nevertheless, I think in that spirit, we often grumble that we have too few opportunities to actually think about science and to study the literature. And now we've got that opportunity, and it's very much in that spirit that I give this webinar today, having had time to maybe look at the literature and contemplate things in a way that wouldn't normally be possible. So I'm just going to get my presentation going here. Okay, so I'm going to talk today about cooperative catalysis. I think this is a theme which spans all of the catalyst community. I think too often we break ourselves into different silos, and so I wanted to find an area where maybe we can join together the different aspects of what we do. So I'm going to start off maybe with almost a short tutorial about what cooperative catalysis is. A brief section actually on some of the research from my group, but then trying to put this in context with other literature from across catalysis and maybe look for some connections that we all have. So a good place to start would seem to be with a definition of cooperative catalysis, and actually this turns out to be rather difficult. There's not one universally agreed definition. A quick look in the literature shows that there are really two camps here. I think there's one camp really from the organic community looking at synthetic methodology, where they're contemplating cooperative catalysis to be two catalysts and two catalytic cycles working in concert for a single transformation. So if you like, two catalysts working in parallel. And then there's the second definition, and actually the one that I'm going to spend most of the time on today, which is one catalyst and one catalyst cycle, but actually the substrate activation across two different sites. And compare this to traditional catalysts, where we have one catalyst site. I think it's on one catalyst cycle. I think it shows that maybe sometimes we're always trying to focus on having single site catalysts, and by that we often mean a single atom, whether that be supported by ligands in a homogeneous catalyst or by some sort of support in a heterogeneous catalyst. That can be a very powerful way to generate catalysts, but in fact there are other possibilities, and some of those other possibilities in terms of having multiple sites can actually be more useful. So briefly, I was going to talk about this first definition for a short while, the one used more by the organic community. So I think in this definition, In this definition where we have two catalysts, two cycles working in concert. So imagine a simple transformation where we have A reacting with B to go to C. So in traditional catalysis, and if I come here to the bottom left, you can see in traditional catalysts, we would often activate one of the substrates. So here I've shown in some way we're lowering the energy of the LUMO of A. And then this reacts with B, so we've got a lower energy barrier here and we catalyze the reaction. In this type of cooperative catalysis, rather than just activating A to A prime, we also activate B to B prime. So in this case, we're raising the energy of B to B prime. And you can see actually the energy gap here then becomes lower. So this should help the catalysis. So even in this area, people use lots of different terms. There's really a problem with the nomenclature here. Macmillan, more in the context of organocatalysis, often talks about this as being synergistic catalysis. Jacobson talks about cooperative dual catalysis. Trost talks about contemporaneous dual catalysis, which I can't even say, so no wonder that hasn't caught on. So this seems a very good concept. That there are potential problems with this, though. There's only one of the challenges around the kinetics. So just looking simply at the kinetics here, we can see if we're generating two intermediates, A prime and AB, via the activated intermediates here, the concentrations of these must be low, and then therefore that means for the to get a good conversion here, to get a good rate of reaction, we need a very large constant here. The rate constant needs to be very large. Now clearly this does work in some cases, so that is maybe less of a problem. More of a problem in reality is that we can often get quenching of catalyst 1 and catalyst 2. We'll see this again later. Quite simply, putting two different catalysts into the same solution, they can react with each other. A third problem is the background reaction. So of course, even if we're just activating A or B, not both of them, that will still catalyze the reaction. In many cases, that won't be a problem, but especially if we want a stereo-specific outcome, then that might affect enantioselective processes and lead to problems. So this seems a very elaborate concept, but there are very well-known examples of this. So kind of household name reactions, things like the Sonogashira cross-coupling is a very good example. So here we have a catalyst cycle based on copper, and the copper cycle is activating an alkyne to give this intermediate, which then reacts with a palladium catalyst in another cycle, in a typical sort of cross-coupling type scheme. So this obviously works very well and is a very good example of this. So here the two reactions are happening in parallel, they're happening simultaneously. Related to this is where the reactions happen in series, and often people would call this a tandem reaction or a cascade process. So here's an example from the Sanford group, where we have three catalysts now working in cascade to convert carbon dioxide and hydrogen into methanol. So obviously a very useful transformation. So this looks very good in principle, but again, there are problems. In particular, there can be problems in terms of the different catalysts working together in the same pot. In reality, actually, the scheme I've drawn here achieves about 2 turnovers. In reality, what you really want to do is, although this looks good on paper, is to separate out the different catalysts into different reactors. Often, although there's a higher cost in terms of the infrastructure in doing that, you get much more control by separating this out into different stages. So that was the first definition of cooperative catalysis. The second definition, the one I'm going to focus on today, is one catalyst and one catalyst cycle, but the substrate activation across two sites. So again, let's look at a general reaction scheme here. So traditionally, at the top, I guess I've drawn a scheme here where we have a metal center, we have X, Y, and in the first step, I've got an oxidative addition of X and Y to the metal center. And then X and Y can be delivered to a substrate and we get a catalytic reaction. So for instance, XY could be hydrogen, the substrate could be an alkene, and that would be an alkene hydrogenation by a classic sort of Wilkinson's catalyst mechanism. If we have a cooperative mechanism, on the other hand, now rather than having a single site, we have two sites, A and B. And now we heterolytically cleave X and Y across A and B. This now can deliver, again, X and Y to the substrate, and we get the same outcome, but this has happened across two sites. So this is an intermolecular example. We could imagine an intramolecular example as well, where A and B, in fact, are adjacent sites on the same surface, or A and B are linked by some sort of ligand framework. Or indeed, as you'll see later, A is maybe a transition metal and B is part of the ligand structure. But we get the same outcome here as the traditional catalyst, but cooperatively this time. Again, there's a problem here in terms of just the vocabulary we use. Even within the homogeneous catalyst community, sometimes this is called bifunctional, multifunctional catalysis. Sometimes it's called ligand-assisted catalysis. Sometimes it's called outer sphere catalysis. Sometimes it's called frustrated Lewis pair or cooperative Lewis pair catalysis, all meaning essentially the same thing. So I'm going to move on now and talk in a little bit more depth about this last area, frustrated Lewis pairs, and in particular talking a short section about some work from our research group that I think is pertinent to this. So first, a brief introduction to this. I think the concept of frustrated Lewis pairs is now very well known. So first introduced by Doug Stephan, what, more than 10 years ago now. And let's maybe take a step back and think, why are transition metals often such good catalysts? And I think a simplistic explanation would be, well, transition metals have orbitals of the right sort of energy that can be filled, or donor orbitals. We've got empty acceptor orbitals, all on the same transition metal. And this means that they can interact with substrates via donor or acceptor interactions. And this means that we can activate substrates and we can do catalysis with them. If now we consider a main group system, well, actually this situation is much rarer in main group systems. In fact, for main group elements, we probably need to separate this out so that we've got a donor type interaction on one center, so a Lewis base with a lone pair. And we have the acceptor orbitals on another center, a Lewis acid. Of course, the problem here is if we take a Lewis base and a Lewis acid together, it's going to be very difficult to react this with a substrate because they're going to want to react with each other. If we take a Lewis base and a Lewis acid, we make a Lewis pair. So here is an example of that. So here we have a highly Lewis acidic fluorinated aryl borane compound. And if you react this with a fairly small phosphine, so triethyl phosphine, you can see that we make a very stable Lewis pair here with a fairly short and strong boron phosphorus bond. So what Doug Stephan described was actually a situation which is known from systems previously to this, and that is that if you start to increase the steric bulk of one or both of these components, although electronically they want to quench, sterically they can't. So if we look at this example, now we have the same boron species, but now we have a much bulkier phosphine. So still a very Lewis basic species, but because of the steric bulk now, the two centers can't interact. So if you like, we've enforced social distancing between the boron and the phosphorus. They've got a social distance of just over 4 angstroms here. Sorry, I tried to think of a better joke about social distancing, but that was as close as I could get. So this is a frustrated Lewis pair. Sterically, they can't get to each other, but electronically, they still want to quench. So this has a very high latent reactivity. So we react these species together, we get no reaction. But if we put a small molecule in there, something like hydrogen, then very rapidly, they will heterolytically cleave the hydrogen and make a species where now we have a borohydride type species with hydridic hydrogen and an acidic species. And so now this is very well set up to deliver a hydride and a proton to another substrate in the way that I described before. And this is where a lot of the utility of these species can come from. I won't go into much more detail, apart from saying that there are a whole scope of substrates that can be hydrogenated with these main group frustrated Lewis pairs. There are still problems. Of course, if the substrate itself is a non-sterically bulky Lewis base, then that can interact with the Lewis acid in a way to quench the reactivity. So there can be some limitations on substrate scope, but now there are some very nice ways to get around that and fairly broad scope in this area. So my group's small contribution to this area was realizing that this doesn't have to be limited to the main group. And in fact, we can have transition metal frustrated Lewis pairs. So in this particular design concept, we've kicked pretty close to the systems before with a phosphine to be the Lewis base. But now rather than a main group Lewis acid, we have an electrophilic transition metal center. I think this has certain advantages. Certainly synthetically, making fluorinated boranes is a very difficult thing to do. By contrast, changing the ligands on around electrophilic metal centers is quite straightforward to do. Also, maybe we can combine this powerful activation chemistry with some of the other reactions that we have with transition metals, such as oxidative addition and so on. So this was our original design concept. Let me show you one of our catalysts here. So this time we've got a CP group on the zirconium. So in fact, we do get a zirconium phosphorus bond here. It's a fairly long bond, but we've got a persistent interaction between zirconium and phosphorus here. The phosphorus NMR is very useful here. So the free ligand CO2. It will react with CO2 as well to give this species, and then finally it will react ring open with compounds such as THF. So this is very similar to a main group frustrated Lewis pair, but showing that we can have the same sort of concept using transition metals. So one of the problems with our original work is that actually these intramolecular systems are rather difficult to synthesize. In particular, what we want to be able to do is to change the R groups here, so we can vary the sterics and electronics and so on. And that turns out to be rather difficult to do. So what we can do is move from an intramolecular system to an intermolecular system. This time making this, this zirconium alkoxide species or aryl oxide species, very straightforward to do, 3 steps from commercially available materials. And then of course we can react this with any commercially available phosphine or indeed other Lewis base that we choose. So this is a nice way to look at a much broader range of potential catalysts. Here are the structures of the Lewis acid components. You can see that when we have CP rings here, actually we get a weakly coordinated chlorobenzene molecule, and we get a pseudo 3 coordinate compound with CP star ligands. And now we can start to look at the interaction of these with various phosphines. So we've got several phosphines here in order of increasing steric bulk. And just to remind you that the phosphorus NMR is useful here. So if we look at the phosphorus NMR for the free phosphine, if it binds to the zirconium, we should see a shift in that phosphorus peak. So let's look at the CP Lewis acid for a start, the CP zirconium Lewis acid. You can see that for triethylphosphine, triphenylphosphine, and tricyclohexyl, we're getting clear shifts in the 31p NMR. So in these cases, they are binding to the zirconium center. For the bulkier phosphines, we seem to have a frustrated interaction. If we move on to the CP star derivative, actually in all cases here, we see no shift in the phosphorus NMR, suggesting that we've got a frustrated interaction in all cases. So that seems fairly clear, but actually what surprised us was when we looked at the reactivity of these species. So when we looked at the reactivity of the species where we have CP ligands, but fairly small phosphines, these also show frustrated Lewis pair type reactivity. They seem to be behaving as frustrated Lewis pairs, even though this would indicate that we have some sort of persistent interaction. And that led us to a technique which I think could be quite useful in this area, and that's looking at DOSI, or diffusion ordered spectroscopy using NMR techniques. So quite simply, this is an NMR technique that allows you to record the diffusion coefficient for a species in solution. If we do this for the CP star compound, you can see in the top left here the diffusion coefficients for the separate species. If we mix these together, since we've got a frustrated interaction, we would expect the diffusion coefficients here to stay roughly the same. We get two distinct species. And that's largely what happened. So there's a slight decrease in both of them, maybe suggesting some sort of interaction. But we do get two distinct diffusion coefficients for these two species. What surprised us was when we moved to the CP analog. So moving to the CP analog with triethylphosphine, let me remind you that this seemed to give a classical Lewis pair. And what we would expect there is these to coalesce to a single diffusion coefficient for the one species. In fact, that doesn't happen. Certainly we get a dramatic decrease in the diffusion coefficient for the phosphine, but it's still different to that of the zirconium. So I think what's going on here is that actually we have a dynamic equilibrium between the species. In fact, although the equilibrium may lay far over to having a classical Lewis pair, so long as we have a small amount of the frustrated pair in equilibrium with that, that frustrated pair can react and can give us catalytic results. And I think this means that maybe there are many examples out there that at first glance look like classical Lewis pairs, in fact may show frustrated Lewis pair type reactivity. Let me move on quickly to talk a little about catalysis. So we've in particular looked at dehydrogenation or dehydrocoupling catalysis here with amine boranes. So a widely studied reaction, and these catalysts work quite well for the dehydrocoupling of amine borane to give this cyclic dimer type compound. If we remove the phosphorus, we don't get any catalysis, so it is behaving as a frustrated Lewis pair. And we've done extensive mechanistic studies on these. I won't go into a lot of detail. Actually, you know, people talk about amine borane as a hydrogen storage material. I think in reality, it's just a very nice substrate in that it gives you lots of NMR handles to study the mechanism of reaction. And that's exactly what we've done. So we can look at this initial sigma compound between the amine borane and the zirconium, and we've characterized that. This will then dehydrogenate and off cycle give us the cyclic dimer. Actually, the compound here, which is the hydrogen activation compound, this is rather thermodynamically robust. So you can heat this up to over 100 degrees and it doesn't lose hydrogen, but it is kinetically labile, and you add another equivalent of the amine borane substrate and it loses hydrogen and we get turnover. So there's an example of a transition metal frustrated Lewis pair doing catalysis, but I think that actually this concept goes much broader than homogeneous catalysis. Here's an example, 20, 30 years before Stefan came up with the concept of frustrated Lewis pairs from the classical heterogeneous catalysis literature, looking at active sites for hydrogen absorption onto magnesium oxide. And you can see this 40-year-old study shows that hydrogen activates on the substrate, on the surface of magnesium oxide in a way that looks very reminiscent of a frustrated Lewis pair. We've got a Lewis acidic center on magnesium, we've got an oxygen center, and we get heterolytic cleavage across these two. Now, of course, this is, if you like, a pristine surface, and people from the heterogeneous community will recognize that often defects in surfaces can be very potent sites for catalysis. And more recently, people have started to exploit this and really look at frustrated Lewis pairs in this context. So here's an example from Jeff Ozin looking at indium oxide surface frustrated Lewis pairs. This time we have, if we have a defect in the surface here, what this does is generate a more Lewis acidic indium center, and adjacent to that, a more Lewis basic oxygen center. And when you add hydrogen to this, you get very good evidence that this adds in a very frustrated Lewis pair type way to give us activation across the indium and oxygen sites. I think an even nicer example from this group looking at surface defects in Syria. So this in a very elegant study combining experiment and theoretical work looks at how having a defect in the Syria, it's rather small here, but looking at the second line here, this defect actually greatly lowers the energy barriers for heterolytic cleavage of hydrogen in this particular species. Note here in the bottom right, the diagram they draw into how this might happen. So we have some sort of initial interaction with the cerium, a sort of side-on interaction with the sigma bond of the hydrogen. And then we have a side-on interaction with the oxygen. And just bear that in mind for something I will talk about later in another area of catalysis, which again looks remarkably similar to this. So now people are starting to use FLP type terminology in the heterogeneous area, but can we take this further? Are there other examples? And in particular, I was struck by the area of hydrogen spillover. So people will recognize that hydrogen spillover is widely recognized in catalyst. It is somewhat controversial in some areas as well. And just briefly by way of introduction, what happens here is that we would have some sort of supported metal. So the metal typically would be something like copper or palladium. And that copper or palladium will absorb, activate hydrogen. So we get hydrogen cleavage on the metal here. But now we get migration of these H species onto the surface. We get spillover onto the surface. So this, as I say, this is controversial in some areas, in particular for non-redox active supports. The thermodynamic driving force by which this migration happens is somewhat uncertain. But it is implicated in many catalyst systems. And I think one good example would be copper supported on zinc oxide or zirconium oxide for methanol synthesis. So just looking at this methanol synthesis literature. So here's a diagram I've stolen directly from the first citation here. It's a Bell paper looking at how hydrogen spillover can activate it. So I think looking at this as an organometallic chemist, there are things that I disagree with here. Certainly drawing oxygen-bound carbon monoxide is something that looks very uncomfortable to somebody from an organometallic background. But I think what is noticeable here maybe is how the activation of CO seems to happen on a zirconium. In fact, Bell even draws a defect in the structure of the zirconium oxide here. So we've got a more Lewis acidic zirconium and a more Lewis basic oxygen site. So this gives us the binding of the CO, activation of CO, and then we get cleavage of hydrogen on the copper species, which then spills over onto this surface and hydrogenates the CO, the bound CO, down to make methanol. So a few interesting things for this, looking at this more from with my background as a homogeneous catalyst chemist. The first is this activation of CO, which looks very much like frustrated Lewis pair chemistry. Second is the fact that hydrogen spillover is known to be limited largely to proximal supported sites. And there's very good evidence, in fact, that the catalysis is occurring at the interface between the copper and the support material. Well, that looks to me like very good evidence that, in fact, this is cooperative catalysis, that the active site here is not a single metal site. In fact, it's some sort of multi-metal oxygen site on the interface between the two. And it's also made me look back at some work that we've done in the past, where actually in homogeneous systems with the transition metal frustrated Lewis pairs that I showed you before. So we found that if we bind CO to one of our transition metal frustrated Lewis pairs, in fact, we get this very weakly bound carbon monoxide complex. This is a very unusual complex. It's unusual to get CO binding to a D0 metal center like this. And in fact, the stretching frequency of CO is higher than that of free CO gas. So it's a non-classical CO. If we take this CO compound and add hydrogen, or in fact, if we have a mixture of CO and hydrogen, what we find is that we get a species which looks very much like the species that Bell was suggesting for methanol synthesis. We've activated the CO, we've added hydrogen to it. You can see, okay, we've got the Lewis acidic zirconium here. Rather than a Lewis basic oxygen on a surface, we've got a phosphine, but the same principle holds. What it's made me realize, looking back at this hydrogen spillover work, is that maybe we should take this species and look at adding hydride and proton to this from a second catalyst in the way that the methanol synthesis catalysts seem to work. I think that's certainly an experiment when we're allowed back into the lab that we'll have to investigate. So maybe this frustrated Lewis pair concept goes further than just homogeneous catalysts. But let me look now at another area, which hydrogen transfer reaction, so hydrogenation, dehydrogenation. Again, I think this is something where maybe we're talking about the same thing, but there's a problem with the vocabulary. So let's look at the classical Wilkinson's mechanism, very well known, all happening on the same metal, oxidative addition, migratory insertion, and so on. But in fact, emerging as a possibly even more important type of catalyst in some areas are the so-called outer sphere hydrogenation catalysts. So here the active site is not localized on a single metal. In fact, the ligand itself is part of the active site. It's a cooperative catalysis. The ligands are also controlling the sterics and electronics, but actually the active site here is the ruthenium and nitrogen together. Very similar to that magnesium oxygen support we saw for activating hydrogen before. In fact, one of the key steps is where we take the ruthenium nitrogen bond, we heterolytically cleave hydrogen across that in a very similar way. This can then deliver hydride and a proton to a substrate, and we get catalytic turnover. So many catalyst structures here, many of them are household names, so the Nuyori type catalysts, some of the pincer compounds popularized by Milstein and Bella and others as well. You know, these are really the state of the art when it comes to asymmetric hydrogenation with polar substrates. And just looking at the Nuyori catalysts by way of example, so I won't go into detail of the catalyst cycle, it's exactly the same as before, but you know, beautiful design of the catalyst here with this cooperative type mechanism to give a wide substrate scope and really excellent EEs in this case. So this is the catalyst cycle, but let's maybe take a step back and look at some of the initial interactions here. Because this is an older study, so this is from the 1980s from Bob Morris, looking at the pKa of hydrides of this type. So the pKa of hydrogen dissolved in THF is about 60. So it's going to be difficult to deprotonate hydrogen. However, if we bind hydrogen, molecular hydrogen, to a metal center, such as the iron center here, now this bound dihydrogen is deprotonated by a simple amine such as triethylamine. So the pKa of this bound hydrogen must now be about 12. And in fact, now in activating this, you can see this is very similar to the steps in the Neyori type catalyst. Bear in mind, this looks very similar to that slide I showed you about the activation of hydrogen on the defect on Syria. There, we'd got bound hydrogen in the same sort of way. That would lower the pKa of that hydrogen, and then in that case, it was an oxygen that came in on the surface to deprotonate, but exactly the same sort of concept. What's important here is that, of course, we can vary the pKa of this bound hydrogen by varying the other ligands around the ion. In particular, if we put electron withdrawing ligands on iron, good pi acceptor ligands, things like CO, that should lower the pKa of the bound hydrogen. And this is something that Bob Morris has explored in some very nice work going from ruthenium to iron catalysts here. So again, as good as the Neyori catalyst now, but based on iron rather than ruthenium. And a key feature of this catalyst is of course, the rather elaborate tetradentate ligand, but also this CO ligand. A very simple ligand, one of the simple ligands we often ignore as homogeneous catalyst chemists. But this is crucial to get catalytic turnover here. And you can imagine what this is doing. A pi acceptor ligand, it's lowering the pKa of any bound hydrogen and making that easier to deprotonate by the amines in the ligand structure. And those of you from the biocatalysis community, this will look very familiar because the structure of this catalyst really isn't a million miles away from iron-iron hydrogenase type catalysts. So if we look at the active site for one of these catalysts, you can see there's a rather elaborate ligand structure here. But the mechanism which is well established now by which these operate is that we bind hydrogen, as you can see in the top left. By binding hydrogen to the ion center, we now lower the pKa of that, and it can be deprotonated by a proximal base residue somewhere in the ligand, and then we get heterolytic cleavage and catalytic turnover. Note also that we've got exactly the same sorts of small ligands on the ion here. We've got CN, we've got CO. Actually, nature has evolved to have exactly the same sorts of ligand sets that the more recent catalysts have designed to get a more electrophilic metal center and easier deprotonation of the bound hydrogen. So that's starting to draw together, I guess, the strands that I wanted to talk about this afternoon. And really the main message here is, aren't we all just talking about the same thing? So even in the homogeneous catalyst community, some people talk about frustrated Lewis pairs, some people talk about outer sphere hydrogenation. In fact, it's a very similar process, maybe even the same process, where we heterolytically cleave hydrogen across a nucleophilic and electrophilic center. But this goes further as well. In the heterogeneous area, surface defects are very well known to be potent catalytic sites. And many of these defects will generate more Lewis acidic sites in close proximity to Lewis basic sites, with those two sites frustrated because they're locked into the surface. Maybe on interfaces as well between metals and the surface, we can imagine a very similar sort of interaction that maybe helps explain other areas. And certainly in biocatalysis, it's been very well known for a long time that basic residues in close proximity to metals are crucially important in terms of catalyst cycles. And this is one of the crucial ways that nature largely uses first row transition metals for catalytic processes in a way that we're now trying to recreate. So really, to conclude, I think there are three messages I'd like to finish with. The first is that really catalysis is one large community, and it can be unhelpful sometimes to split that down. I think sometimes, more than anything, we're just separated by nomenclature. I think this area of cooperative catalysis, there are many things that we talk about that are exactly the same, but even within small sub-disciplines within catalysis, we use different vocabulary, and that tends to separate us rather than bring us together. And finally, perhaps most importantly, I think cooperative catalysis is a very powerful concept. it can be a powerful concept in how describing and understanding existing catalysts. And I'd certainly encourage people to think in terms of this way in looking with fresh eyes at existing catalytic processes. But it can also allow us to design new types of catalysts, building multi-site type functionality into the catalyst by design. So that brings me towards the end of what I was going to say. I just want to finish by thanking the people in my group that did the work on the brief section on frustrated Lewis pairs I talked about, particularly Andy Chapman and Owen Metters. I'd like to thank the Catalyst Hub for giving me this opportunity to talk to you all this afternoon, and thank you everyone for listening.
Thank you very much, Duncan. That was very interesting. If people would like to give Duncan a round of applause through your reactions, please do. I think as most of us are muted, you can clap if you've got your video.
I'm happy to take virtual applause. Thanks very much.
So yes, thank you very much for that. If people would like to indicate a question or put a question in your chat, please do. Please don't just shout out questions, because it will get very confusing with over 200 people on. So if you put a question in your chat, we will call on you, or you can type your question in and I'll read it out. Do we have any questions?
Hello.
Please indicate your question in your chat. Don't just call out. Lots of people saying thank you on the chat, Duncan. Does anyone have a question? Everyone's holding back at the moment, I think. So Joe Rennie has a question. Joe, if you'd like to ask your question. So it's on syngas activation.
Hi there, sorry, yeah. Hi, Duncan.
Hi, Joe.
With the syngas activation and the frustrated Lewis pairs, obviously when you look at CO and hydrogen on its own, you know what's going on. And I guess the assumption is that it's happening at one nuclear center. Have you got direct evidence for the order of events? So is it CO first or hydrogen first? And is it happening just at one center, or does it involve more than one molecular entity?
Thanks, Joe. It's an excellent question. So just in case people didn't hear Joe's question, it was asking with the syngas chemistry, so the hydrogenation of CO, is this happening at one metal center or one active site, or is it happening across two species? And also, what's the order of events? I think the honest answer is we don't know. I think in researching for this lecture, it's made me look back on that chemistry with fresh eyes and make me realize that we do need to investigate that a little bit more. Clearly, there is a possibility there that in fact we have CO bound across one frustrated Lewis pair, and then in a more bimolecular reaction, actually hydrogen activated at another frustrated Lewis pair, which delivers a hydride or a proton to that CO. I think, you know, we need to go away and think carefully about what the experiment might be to distinguish between those possibilities. I think, again, though, what struck me was just really the similarities between that and some of the surface chemistry that people talk about. You know, we didn't do that chemistry thinking about models for surface reactions at all. And yet I think looking at that in slightly more depth, it could be a very good model for that.
Thanks, Duncan.
Okay, thanks, Joe.
So Donato has a question. Do frustrated pairs only work on the hydrogenation reaction? That
is, again, a good question. So the vast majority of the literature has been looking at hydrogenation. I guess the first reaction here was the heterolytic cleavage of hydrogen, and there's been a lot of work there. I think there are other reactions though, and I'd draw your attention maybe to some of the beautiful work from Eugene Chen and others looking at polymerization catalysis with frustrated Lewis pairs, where I think there's some very nice work there showing how you can get very good control over polymer microstructure using frustrated Lewis pairs.
Thank you. I hope that answers your question, Donny. Rashmi, sorry if I've pronounced that wrong, is asking how you prepared the magnetic heterogeneous catalysts.
Okay, so I should point out that all of the heterogeneous work in there is not our work. This is work that I've done from I've taken from the literature. So the homogeneous zirconium phosphorus work was ours. The rest is from literature papers. I guess I've been careful to cite everybody's work as I've gone through. So I'm sure if you go back and look at those citations, you'll be able to find the methods by which they made those.
The next question, sorry, it's scrolling quite fast. There's a couple of thanks for a very lovely presentation. There's a question from Leanne on the progress in CO2 activation on FLPs.
Yeah, so CO2 is an interesting one. CO2 as a substrate seems set up for binding to frustrated Lewis pairs. You know, the fact that it's a kind of, I guess, a ditopic type molecule, and they bind very well to frustrated Lewis pairs. There is some work in the literature reducing CO2 down. The problem is it tends to be using hydrogenation reagents, which are much more complex than simple hydrogen and are certainly not economic. My feeling is that actually it's an area well worthy of further investigation. I think it's also an area that when you look at some of the methanol synthesis catalysts, which of course CO2 is implicated as an intermediate in very many of those, that I think a lot of the chemistry there actually could be described in frustrated Lewis pair type terms, even though these catalysts are 20, 30, 40 years old.
Okay. And then there's a question about commercialized. What are the commercialized FLP catalysts? Do you have any understanding of that? Any knowledge about that?
Yeah, less knowledge of that. I mean, probably the closest to that would be Doug Stefan's work, more in some of the sort of fine chemicals, pharmaceutical methodology area, looking at some of the fluorinated boranes in various transformations. Of course, that fluorinated borane is commercially available already. So I know that's being used in many synthetic labs now for various hydrogenations.
So Dimitri has a question. Dimitri, would you like to unmute yourself and ask your question?
Hi, Duncan.
Hi, Dimitri. Good to see you.
Yeah, Duncan, I have very popping up in my mind question. Are there any heterobimetallic complexes that work as FLPs?
Thanks, Dimitri. Yeah, it's a good question. The answer is there are. So we've looked at some zirconium platinum type systems. So platinum as the Lewis base. There's other work in the literature as well, looking at some gold systems with other transition metals. So I think it's a growing area where people are looking at two different transition metals. Of course, there's a huge literature going back to sort of the 1970s and 1980s when heterobimetallic compounds were very well investigated, more as fundamental organometallic compounds. And I do wonder if some of those are worthy of reinvestigation in terms of their catalytic properties with the sort of the new insights in terms of frustrated Lewis pairs in mind.
Thanks, interesting.
So Bolan Wang has asked, how do you think the heterogeneous metal-free LFPs activate hydrogen?
I'm sorry, I've lost that one. Can you just repeat that one again, Josie?
How do you think the heterogeneous metal-free FLPs activate hydrogen?
Again, so if this is the sort of the 1983 paper, I think probably if you were to reinvestigate that, I wouldn't be surprised if actually, again, surface defects were involved rather than a pristine surface. Looking at the work that's coming out on indium oxide and the Syria, it does seem as though those defects are very important. And you could imagine how a defect in those sort of magnesium oxide surfaces could greatly enhance the Lewis acidity of the magnesium and the Lewis basic component. So I think, again, maybe it's an area that's worthy of reinvestigation. Sorry, Josie, I think you're muted. You're still muted. Oh, you're back with us. Sorry. Can you say that again, Josie? You were just muted.
The dog started barking, so I pressed. Patricia asks, how much could you elongate the bond to catch the hydrogen molecules? If you could form a tetramer, for example, the elongation of the bond should reach a minimum to be able to allocate as much hydrogen as possible.
Yeah, it's an interesting point, isn't it? I mean, I guess I've not thought about that in detail. Clearly, I mean, again, there's a large literature on metal hydride species and the extent to which they can be thought of as dihydrides versus molecular dihydrogen compounds. And I think all of that literature is pertinent to this area in terms of understanding what possibilities might be there.
If I take just one more question, and apologies to anyone if I've missed your question, hopefully it's been answered elsewhere. So what are the possible applications for the cooperative catalysis?
Okay, well, I think, look, there are many applications. I think, if I talk about a subject close to my own heart, I think increasingly as we look to maybe more renewable feedstocks rather than the traditional sort of fossil fuel type feedstocks, very often those feedstocks are the sorts of things that have polar functionality in them, or oxygen functionality in them. They're the sorts of things that nature's catalysts, biocatalysis, work quite well with, and we've seen that they often use cooperative type mechanisms. So I think, substrates like CO2, biomass, and so on, I think cooperative catalysis is a very, potentially a very powerful area for that sort of substrate.
If you're happy, Duncan, I'll probably draw it to a close there because I'm just conscious of time. Thank you again for an excellent talk. Just the number of questions we've had shows how engaging it was. We had a few more questions, but hopefully some of them have been covered in other answers. I tried to pick ones that were slightly different, but I should say,
Josie, if people want to send me an email, and if they didn't have time to answer their questions, I'm happy to answer by email or set up another meeting if people want to talk.
Okay, thank you for that, Duncan. That's very useful. And thanks to everyone for coming to this first Catalysis Hub. My internet dropped out in the middle. It was the one scenario we hadn't planned for, but hopefully that didn't cause problems for anyone else. And hopefully the recording has saved and continued. So I will try and get that up. And apologies if my internet has caused any technical problems. You're getting lots of thanks on the chat, Duncan, and some comments on missing the CCI. I will just share my presentation because we have the next webinar is scheduled for the 28th of May at 3 o'clock, and it will be Professor Andrew Beale, who is an inorganic professor at UCL and co-founder of Finden, which is a spin-off company, and he'll be talking about some of his work on the Harwell campus and some of the applications of that. My contact details are up there and how to join the Hub mailing list. For information on more. The webinar page is live and we will get a title up there as soon as possible. So I will just say thank you to everyone. I have got that there, and goodbye.